if we understand that this is our point x naught, y naught, f of x naught, the point where we're starting, I'm not going to label the coordinates of that point because I want to label this picture and don't want a lot of extraneous labeling. But we understand that this is our original point. We move 0.05 units in the y direction, 0.1 unit in the x direction. So I'll call this delta y equals 0.05, and I'll call this delta x equals 0.1. Nothing is to scale. This is purely representation of the behavior in this region. So I'm going to draw a right angle here, a right angle here with vertical, draw a similar line length equal to this one, line parallel to the x-axis. Designate these by right angles. You've seen this picture before, but I'm labeling it for the specific function we have here. Okay, so here's some more right angles. And we have a box. Now it's not very well drawn, but this is regarded to be a completely rectangular box, so all these vertical sides are 270. All the sides in the y direction are 0.05. All the sides in the x direction are 0.1. As we've seen, delta y equals 0.05 with fy equal to 16 leads us to the triangle we see here with a side 0.05 here and a side of 0.8 here. Again, these are not to scale. And here's the delta f due to our change in y. Now over here, x changes by much more, and I'm going to at least make the change in the f changes by much more due to the larger change in delta x and also the greater partial derivative in the x direction. The partial derivative is 28 as opposed to 16, almost twice as big, almost twice the change in x. It's going to give us almost 4 times the change in the value of the function. So we're going to come up here about 4 times this far. Not actually going to be able to come up quite that far, but let's come up about here. Okay, so here's a triangle with sides of 0.1 to 0.8 and a slope of approximately 28. Now, over here, if we move from here to here, what happens? Well, the value of the function has to go up by about 0.8 because the y derivative here is assumed not to be too much different than the y derivative here. So I'm going to have to come over here this distance so that I'm directly above this point. Then we're going to have to come up 0.8 units here so that this triangle again has side 0.05 and a rise of 0.8. Now I came up a little too far here and I'm out of paper, but I'm going to kind of cheat and go up on another piece of paper so that this triangle is similar to this one. Now if we start from this point, we climb 2.8 units to get here. If we went at a level, we'd still be 2.8 units above this point, but we go another 0.8, so we climb a little bit more, and now we're 3.6 units higher than we were when we started down here. Picture is going to get a little messy, but I'm going to try to keep it straight. Okay, now this edge is parallel to this. And if we move from this point parallel to this line segment, we'll be above this corner of our original square when we get to this point. Now, how far will we be below the top point here? Well, this triangle, if we assume again that the value of our x partial derivative doesn't change a whole lot when we move from here to here, this triangle should be similar to this one. And we'll have another triangle here where we have a 0.8 here, 2.8 here, and this triangle is similar to this one and to this one. Might be a little difficult to see exactly what should be shaded, what shouldn't. I've got a lot of extraneous lines here. But the top of this picture is going to consist of a plane, a part of a plane. So let's try to shade that like so. And we're actually kind of looking at this from underneath. This is like a roof that's sloped a little bit in this direction and a little bit in this direction as viewed from beneath. At the risk of completely messing up the picture, let me trace over a couple of similar triangles. Okay, we've got this triangle here, which is presumed to be geometrically similar to this triangle. So this triangle is about the same as this triangle, and they don't look too much different. The only difference between this triangle and this triangle as far as the value of our function is concerned is that it starts 0.8 of a unit higher, because starting from this point, if we come over to horizontal, for 0.05 units we've got to go up 0.8 units. So this point is 0.8 units higher than this one, so this triangle is 0.8 units higher than this one. This triangle started at the level of our original point and went up 2.8. This one will start at a level 0.8 units higher than that and go up 2.8 units, giving us a total change of 3.6 units from here to here. We have a 0.8 here, a 2.8 here. The 3.6 is the change in the value of our function from this point. From this point to this point, the value of the function changes from this to this. This triangle back here resulted from our y partial derivative. We saw that by going over 0.05 units at slope 16, we go up 0.8 units. And a similar triangle occurs here. And I even drew one up here. Once more, the difference between this point and this point is the 0.8 we have here and the 2.8 here, 3.6. This point is horizontally connected to this point, which is horizontally connected to this point, so from here to here there's no change. Excuse me, it's allergy season, my voice caught. No change in the y value between this point and this point. Change in the y value occurs here. So we conclude that our fy delta y is 0.8, fx delta x is 2.8. And we calculated these numbers by multiplying the y partial derivative times the change in y and the x partial derivative by the change in x. These changes accumulate here, so that between the level of this point and the level of this point, we have a total delta f, which is equal to fx delta x plus fy delta y, 2.8 plus 0.8, 3.6. And that's our delta f from here to here. This expression, delta f equals fx delta x plus fy delta y, anticipates what we call the differential of f, and we'll be seeing that terminology shortly. This picture can lead you to an understanding of this terminology. Once more, this is a picture of what happens to the value of the function f in a small neighborhood in the vicinity of our original point.